Well, we're in Chapter 10, Correlation and Regression, and we're just going to have two of the sections that we're working in this section, in this chapter. We're going to do scatter plots and correlation and regression. So let's go on. We'll look at drawing a scatter plot for a set of ordered pairs, computing the correlation coefficient, testing a hypothesis, just like we kind of did in Chapter 8, and looking at equations of regression lines. In addition to hypothesis testing and confidence intervals, inferential statistics involves determining whether a relationship between two or more variables, whether they're either numerical or quantitative, exists. Is there really a relationship or not? Correlation is the statistical method used to determine whether there's a linear relationship. Now, there can be other kinds of relationships. There could be quadratic relationships where it makes a parabola, the basic plot. But all we're going to worry about in this is a linear relationship. So we're looking for the data as you plot it on a graph to look basically to trend in one direction or the other in the shape of a line. Regression is a statistical method used to describe the nature of relationship. It can be positive, negative, linear, or nonlinear, and there can be no relationship. And so we're going to answer these questions. Are two or more variables related? If so, how strong is that relationship? What type of relationship is there, and what kind of predictions can be made from the relationship? So first, are two or more variables related, and what is the strength of those? We use something called a correlation coefficient, and that's something you need to know. It's a numerical measure. Your calculator can help you find this, but there's also a formula, and it's going to determine whether two or more variables are related, and it determines the strength of the relationship. If the relationship is strong, yes, we say they're related, or there's a correlation. If it's not strong, then we say there's really not much of a correlation between those two variables. Now, there are two types of relationships, simple and multiple. In a simple relationship, you have two variables, usually graphed x and y on a regular graph. You remember how when you graphed coordinates, there was an x and a y. The x was the independent or the predictor variable, and the y is the dependent or response variable. Usually the independent variable causes a change in the dependent variable is how that works. In a multiple relationship, there are two or more independent variables, and they predict one dependent variable. We're going to be worried only with the simple relationship in this section. And what kind of predictions can you make? Well, there's lots of predictions that are made all the time using statistics, weather forecasting, stock market analysis, sales predictions, crop prediction, gasoline price predictions. Futures markets are based on predictions. Some predictions are accurate, some are not accurate. You know, the BCIS was using a lot of numerical inputs to predict matchups, whether you agree with that or not. There was an algorithm formed, and it was, predicting matchups based on a lot of variables, not just two. And the stronger the relationship between variables, the more accurate the prediction is. So in 10.1, we're looking at scatter plots and correlation. A scatter plot is just a graph of ordered pairs, and remember that's an x and y. And when you get data, you get a data for, say you're testing something, say you're testing fertilizer and growth. Well, with one fertilizer value, you get so much growth. And with another fertilizer value, you might get another growth. Well, that's your x and your y variables. Independent is x and dependent is y. And they're graphed on an axis. A lot of times all you see is the first quadrant. Remember, let me go back. When you graph, typically your coordinate plane looks like this. And you have x and you have y axes. And you have your first quadrant and your second quadrant and your third quadrant and your fourth quadrant. Well, most of the time in data, when we're looking at data, we're just looking in this first quadrant. So your graph, instead of looking like that, is just going to look, like this. And you're going to have your independent variable here and your dependent variable there. So here's some examples. This is example 10.1 on page 536. You're going to construct a scatter plot, so you're going to draw the data, and you're going to label your XY axes. So you're going to draw like this, and you're going to have X, and you're going to have Y, and you're going to put your title of your graph up here. And you're going to plot each of these points. So your X is cars in 10,000s. I didn't mean to do that. Okay, so we're going to have cars here in 10,000s, and my next slide is going to have a lot better graph. And the other variable is revenue in billions. So here you've got revenue, or you could put a dollar sign probably, and you're going to have it in billions. And you're going to take each of these points, and you've got your marks that you're going to put on your graph, and if you use graph paper, you have a grid already there. And so at 63 and 7 billion, so say we're counting these by tens, 10, 20, 30, 40, 50, 63 is here, and 7 billion, 1, 2, 3, 4, 5, 6, 7 up here, and 63, you're going to have a dot saying here somewhere. And you plot each of these pairs of data. So this is your X, and the number of cars you sell is going to result in how much money you make. So you decide which goes on X and which goes on Y, and you plot them. And this is what it would look like when you do a better graph than what I was doing quickly by hand there. And you can see that this says it's a positive relationship. And the reason is that if I was going to draw a best fit line through here, a line that best fits means that you're trending through most of the data, it would go something like this, perhaps. That would be your line of best fit. And that line of best fit is leaning to the right, and so if you remember from algebra, that's a positive slope. And when it has a positive slope, that means that we have a positive relationship. Whoops, I see what my problem is. I'm still on the line. Get rid of those. Go back to the pen. Okay, we have a positive slope. And so that indicates that these are have a pretty good linear relationship, sales versus revenue, and it's a positive relationship. Here's another example, page 537. And again, draw and label the x-axis, plot each point on the graph. We've got absences versus final grades. Students, we've got 1, 2, 3, 4, 5, 6, 7 students. And how many absences versus their final grade? Well, it's obvious. You can see the ones with a lot of absences have a pretty lousy grade, and the ones that have been there have a much better chance of making a passing grade. So we've got this trend. Now we have this number out here that's kind of off the basic trend. The basic trend kind of runs through here. If I was going to look at the graphs. Well, this is a little bit of an outlier, but you can include it or not. But if you look at most of the data, it follows along this line. Now, if you're doing these in your calculator and calculating regressions, it's going to give you a line that best fits your data. But again, this is a negative relationship, and again, because that line has a negative slope, we say that it has a negative correlation. The higher the number of absences, the lower your grade, by and large. And so here we have another example, 10.3, age and wealth. And so we're going to see if there's any correlation. Put it on a graph, label your X and Y axes, and plot each point. And we see there's really no trend. Look at this data. It's kind of all over the place. And so this would be there's no relationship or a very weak relationship between this data. It's certainly not strongly linear in any one way or the other. And so to determine the strength of a relationship, we have this correlation coefficient. And the correlation coefficient is computed from your sample data. And it measures whether there is a good, strong connection between those two variables, a causation between the two, whether one and they're linked. And so one that we're going to use is called the Pearson Product Moment Correlation Coefficient. Well, that's a lot of words. And I might actually ask you a question on the test that's something like, what is the actual name for the correlation coefficient that we use? And that's it. But we typically just say it's the correlation coefficient, R, and the symbol is the Greek letter rho, which actually looks like a P. But on your calculators, it's going to be an R. The population coefficient, again, is I guess that's the difference. That's what I should say is the difference. The population coefficient is the Greek letter rho, but we're dealing with samples, so it's going to be R for us. The range is from -1 to +1. There's a strong positive linear relationship between the variables. If it's going to be a +1 or close to a +1, the closer the better, the closer the stronger. And if there's a strong negative linear relationship, then the R will be close to -1. So here we have some strong correlation. This on the right, this would be a strong positive. This would probably be a +1, and this is going to be a strong negative, a -1. These others are trending. If you put a best fit line in there, you can see it's trending negative, but there's so much scatter around it. This is weaker here. On the left, both of these they're positive trends. This one's a positive trend here. This is a positive trend here. On the bottom, they're negative trends. But these are weaker. And that's terrible handwriting. So let me try to do better. Okay, so these here are weaker on the left. It's a weaker relationship. And then we go to a stronger relationship. As you can see, that very definite linear connection on the right-hand graphs. And so the R value here would be, on the right, would be close to -1. The R values on the left would be something less than negative or +1. And here's the formula, and it's very get this bigger. It's very complicated, but it's really not as hard to do as you would think. What you do is you're going to put your data in a table, and you're going to sum things up, and it'll make it a lot easier. But here you're going to have the sum of the product of the two, the sum of your x's, the sum of your y's. You've got to know your sample size, the sum of your x squareds. And this is something different. This is the sum of the x's squared. This is different. This you square your x's and then you add them up. This you square your y's and add them up here. This you take your y column and square it, the sum of the y column. So you have to be careful to distinguish between those two, the differences between those two columns. N is the number of data pairs, and round to 3 decimal places, and when you get your answers. So here we have car-related company, and we've got, this is the data from when we had our cars sold and income in billions of dollars. Our N, if we look at our N, how many data pairs do we have? We have A through F, so we have 1, 2, 3, 4, 5, 6 data pairs. Okay, here's our x's, and so down here we have our sum. You just add these all up. Here's our y. You added these all up to get the sum of the y. Then we have our xy product, and at the end we get the sum of that. Here's the sum of our x squareds. We squared them, and then we added them up, and here's the sum of our y squareds. You square them and add them up. Now we're also going to need to know the sum. You're going to need to know for your formula the sum of x, all of that squared, which is going to be 153.8 squared. And you're going to need to know the sum of your y, all of that squared, which is going to be 18.7 squared. And so you've got to realize again the difference between these and these. It's going to be a very different number. So let's look at how those go in your formula. You have 6 as your n. 682.77 was the sum of your product of x and y. The sum of your x's times the sum of your y's. Then on the bottom you have n. You square root all of this. You have 2 sets of brackets. In one you have the n times the sum of your x squareds, and then time of the sum of your x's, all of that squared. Anyway, and you do all this, and you find that r is 0.982. Well, that's very close to 1. So that indicates a strong positive relationship. And we could see, if you go back and look at that, let me just flip back real quick. I know this is kind of annoying, but that was a very strong positive relationship. And you could see that had an R value of 0.984, I think it was. And so you can see that that is a strong positive relationship between those two variables. So let me go back where we were. And we're going to have another example. This one is the absences and final grades example. Again, get the sum of all your x's, the sum of all your y's, the sum of your x times y's. Square your x's and sum those, square your y's and sum those. And then remember, these will be squared, those two sums, as you enter that particular part of your formula. N is 1, 2, 3, 4, 5, 6, 7. So N on this one is 7. And you're going to put these in your data, and you see a strong negative relationship, negative 0.944. So this one is equally as strong in the negative direction. And our last example, where we had the net wealth and age, you make your table and you get all these totals like we've talked about. Put them in your formula, and this has a very weak R. And again, we noticed that that was not a strong linear relationship when we graphed that. But it's a very weak negative relationship between the variables, negative 0.176. All right, now we're going to go through and we're going to try some hypothesis testing. This is what we did in Chapter 8, where we had the null hypothesis and checked to see if we should reject that null or not. Null hypothesis means there is no correlation between the x and y variables. And the alternative hypothesis means there is a significant correlation between the variables and the population. And it's using rho, because remember, that's the population. That's the population data is rho, correlation coefficient. All right, we're going to use a t-test, and we have R. We discover our R. N minus 2 is your degrees of freedom this time. And then you have all that R times the square root of your degrees of freedom over 1 minus R squared. And that gives you your t-test for this data. So let's look at an example. And there's two ways you can test. You can test using a t-test, or you can test using table I, excuse me, not table 1. And one of our examples gives that. So this is car rental companies. Test the significance of the correlation coefficient found in example 10.4. Use A as 0.05 and R is 0.982. Your hypothesis, rho is equal to 0, and your alternate hypothesis, rho is not equal to 0, the correlation coefficient. Find the critical value. Well, this you're going to go to table F, which is where you got your t-test data. You're going to use your alpha and your degrees of freedom. Now remember, when you're doing a scatter plot and you have a rho that you're dealing with, not a mu, then you're going to do 6 minus 2 degrees of freedom, n minus 2. So in this case, we're going to look up 4 degrees of freedom and alpha 0.05 and find from the table F that that is our critical value. That's the value, remember, that separates whether we retain the null and say it's valid or we reject the null hypothesis. So here is our critical value listed, and I'll write under here CV because that's our critical value, and we found that from table F, if you remember, and it's a two-tailed test. Now we're going to calculate our t. We have to calculate this t based on the formula that was given to us earlier. N was 6 minus 2, that's our degrees of freedom. Our R was 0.982, so that's here, and then it's again here with the R squared, and we find that our t that we're going to use for our test score is 10.4. Well, that's way up here. It's way beyond 2.776. So it's obviously in the critical region, so we will reject the null hypothesis. Remember, this is our rejection region, and this is our non-rejection region. So summarize the results, always is step 5. There is a significant relationship between the number of cars a rental agency owns and its annual income. So, again, we're testing to see the strength, see whether this correlation coefficient, you're testing that for your hypothesis in Unit 10 or Chapter 10 here. All right, here's another example. And this one is using table I to test the significance. This one you don't really have to calculate a t-test. You're just looking at your R value. And you look up your R on your, based on your information given in the problem. Test the significance at a 0.01 at 0.01 alpha, alpha equals 0.01. So that's not really, let's just kind of fix that. Okay. Go for, and I'll just write in alpha equals 0.01. I think that's better than leaving that uncorrected. So we have test the significance at alpha 0.01 of the correlation coefficient. R equals negative 0.176 obtained in example 10.6. And we have the null hypothesis was that rho is equal to 0, and the alternative hypothesis that rho is not equal to 0. There are 6 degrees of freedom for age and wealth. And remember, we didn't think there was a very good correlation with this data. The value in Table 1, where alpha is 0.01, is 0.834. So that's what we're comparing our R that we found in the problem against. For a significant relationship, R has to be greater than 0.834. So if we're drawing this, and this only works for a two-tailed test, okay, so R has to be greater than 0.834 or less than negative 0.834. And we got that from Table I. And all we have to worry about there is our degrees of freedom and our alpha. And we get a value, an R value that you're comparing. You don't have to calculate a T. So R is negative 0.176. Here's 0. So negative 0.176 is way in here. So it is in the non-rejection region, and so we don't reject the null. What we're looking for in order to reject the null, just like always, is for our data to be out here in these two tails, and it's not. It's somewhere in that non-rejection region. So we do not reject the null, and there is not enough evidence to say there is a significant linear relationship between the variables. And they didn't draw a bell curve here, they just drew the rejection regions out here on each end, and our mean 0 in the middle, and falling, the negative 0.176 falling, obviously still in the non-rejection region. It's the same idea. So, possible relationships between variables. So the null hypothesis has been rejected for a value, and there's 5 reasons that that could happen. Obviously, it could be that there is a direct cause and effect between the variables. X causes Y. It could be that we have it backwards, that Y actually is what causes X. There could be something that happens between variables could be caused by a third variable. And there could be a lot of complex interrelationships that we're not aware of. We're going to discuss these a little farther in the next few slides. And the relationship may simply be a coincidence. So, here's some examples. A direct cause and effect relationship. X causes Y. Water makes plants grow. Poison causes death. Heat causes ice to melt. Those are all we know. Those things, one causes the other. What if it's the reverse is true? A researcher believes coffee consumption causes nervousness. But he might fail to consider that perhaps a nervous sort of person craves a lot of coffee and drinks a lot of coffee. And so there maybe not, but there's always the possibility that it could be a reverse cause and effect relationship. Something could be caused by a third variable. So in this case, the example they give, a statistician correlates the number of deaths due to drowning and the number of cans of soft drink consumed daily during the summer. And he thinks, well, there's a significant relationship there because both are going up in the summer months. But both variables could be related to heat and humidity. The fact that many people are out in the water because it's hot, and many people are drinking soft drinks because it's hot, not necessarily one related to the other. A complexity of interrelationships. Talking about a relationship between students' high school grades and college grades. But there's a lot of other things that are factors in that. The IQ, how much they study, influence of parents, motivation, age, instructors, dedication, work ethic. There's just a lot of things that go into making good grades that are not strictly what they make in high school versus what they make in college, being an indicator of what they're going to make in college. Or the relationship could simply be coincidental. Researcher may be able to find a significant relationship between the increase in the number of people who are exercising and the increase of number of people who are committing crimes, but common sense says that's crazy. There's no relationship. And you could do all sorts of crazy things. You could say, well, something went up, when houses became air conditioned or something. Well, there's a lot of things you could say that, but they're not absolutely, related in any way. Okay, that's the end of chapter 10, or not chapter 10, but 10.1. And we'll go into more scatter plots and regressions in 10.2. And that will be the last section we cover in this course.